this case, okay, we have the circular cross-section area, and we have a velocity. We try to find out velocity profile here. Okay, so velocity profile for this coordinate is the x and okay r. Okay, so this is the cylindrical coordinate. So this is x. Okay, and similar to our formula in the previous year is the z direction. Okay, you have to the z direction is our x direction. Okay, so you're using this. Okay, so we have these two terms survive. Okay, so this is next case. Okay, so we have to try to solve this problem. So this is our boundary, the boundary equation with these two boundary conditions. So for here, okay, we assume partial p partial x is also is a constant. Okay, similar discussion we will have. Okay, this dp dx is a constant or not? Okay, can be get from the flow rate. Since flow rate is related to dp dx, and q is a constant, right? Q is a constant, so dp dx is always a constant. Okay, so we assume here, since we already kind of later, okay, we can prove this. So dp dx is you can assume is a constant. Pressure gradient is a fixed constant. Okay, so here we times r. Okay, this r will be moved to the right hand side equation. Okay, integrate r first. Okay, and then divide by r and integrate r again. So you have to do this. Okay, and then you can get a two integration constant. And the two integration constant can be get from this and this. Okay, so we have two boundary conditions. So you end up with you have a velocity profile like this. So this is the parabolic velocity profile. Okay, so u is a function of r only. Okay, and minus 1/4 mu dp dx, and a is our radius a. Okay, so it's our radius of our tube. Okay, r is the coordinate. Okay, with the different r location, you can find our velocity. Any r location. So that's the velocity profile you have. Okay, it's a function of r. And then we can integrate this ur with area. Area is a 2 pi r dr. Okay, so it's from the calculus, you know, the 2 pi r dr is a small area. Okay, and this is the area we have. Okay, times this velocity with the boundary flow rate. We integrate from 0 to area. So r equal to a, so it will give you this. Okay, we integrate this. Okay, times this. Okay, and integrate r, and you will get this constant. So q is a constant, so dp dx is a constant. So that will be okay. So that will be the kind of the potential flow for the circular cross section. Okay, so we know that before, right? In the undergraduate course. Okay, 在我们大学部有教是。在一个管子里面，它的流场怎么，速度分布要怎么样？ The next, we would like to know what happened to elliptics if the cross section is elliptics. Okay, so elliptics we have the equation like this, right? And the cross section is y squared over a squared plus z squared over b squared equal to 1. That's the elliptic equation. Okay. So A and B, one is okay, it's a longitudinal axis, transverse axis. Okay, 一个是长轴，一个是短轴，对。Okay, so we have this boundary condition. It has a cross section boundary for the elliptics. Okay, cross section. And how? So we try to find the velocity flow field for this, for the flow within this elliptic shape of the cross section. Okay, and how do you find it? Since we know what? We know on the boundary, our boundary what? Velocity is equal to 0, right? So one base, okay, 一个 since our velocity u is what? Is function of the x, y, z, right? U is function of y, z, right? It's not function of x. And also this is y squared, a squared plus z squared, b squared equal to 1. Okay? You know, on this boundary here, this is our boundary, this is our boundary, okay? This is y, right? This is z. This is y, for example. Okay, according to the coordinate system, this is z and y. Doesn't matter. Okay, because this is our a. Okay, this is our a. Right? Distance here, semi-axis. Okay, y related to a, b related to z. Okay. So on the surface here, on the surface is what? I have to satisfy what? This boundary, right? So 1 mass y squared, h squared, plus this squared, h squared should be equal to 0, right? On the surface. So on the every point on the surface should satisfy this. Okay? Every point should satisfy this. And our velocity on the surface, what? Is equal to 0, right? On the wall should be equal to 0. Okay? Because the non-boundary condition. So according to this kind of thing, we may have this kind of case. Okay? Our velocity field is equal to alpha. Alpha is a constant. Okay? Any constant, and this one is on the boundary. Okay, if you have any point on the boundary, our velocity is equal to 0. Okay, that's kind of case. Okay, 这是个猜，我们猜大概这样子。Okay, but may not work. Okay, so we have to check this velocity profile can satisfy this or not. Can satisfy this or not, or this. Okay. Can be satisfy our Gaussian equation. So we only try, okay? You only try. Okay, this is satisfy our boundary condition, but may not satisfy our Gaussian equation. Okay, 我们只是用 boundary condition 去猜，速度场应该大概在边界上面要等于0，所以这个应该等于0，所以速度在 x, y satisfy this on the boundary should be equal to 0 because our boundary is here. Okay, so we should satisfy our what? Our Gaussian equation. This is our Gaussian equation. Okay, this is our Gaussian equation. So Gaussian equation gives you the partial square u partial y square plus partial square u partial z square equal to 1 over mu dp dx. This is our Gaussian equation. Okay, two-dimensional cross section. Okay, and so we take this partial square u partial y square. From here you can find out this. And then partial square u partial z square. From here you can get this. Okay, so this one plus this one should be equal to this and should be equal to this. Okay, so we can find out our alpha. This alpha should be equal to this. Okay, equal to this. This is alpha. So alpha is a constant. As you can see, mu is a constant, dpds is constant, a and b is all constant. So alpha is a constant. Look like if alpha, I set up alpha like this. Okay, substitute into here. This equation or this formula can satisfy our Gaussian equation as well as what? Boundary condition. Okay, so this is the solution we may have. Okay, for the elliptic cross section. 这就是这样猜出来的。OK， 这就是我们流体流经过一个椭圆管子，它的流在管内每一个 YZ 位置它的流场的一个分布情形。So this is elliptic cross section velocity profile. Okay, so we can integrate. Okay, to give the volume flow rate again. Okay, that's you can check, and then. Due to the mass conservation, Q is a constant, and Q also related to dpdx. So dpdx is a constant. Again, we can prove. Okay, pressure gradient is a constant for this closed section. For the straight pipe, okay. Okay, so in the lecture, in the homework, okay, not homework, in the problem set of the textbook 7.3, they also demonstrate you can use it as a triangular closed section. Okay, so it can be work in any closed section. Okay, but you have to be careful. Okay, this is all assume you only have u velocity. So some of the closed section we have the secondary flow. I don't know what do you mean the secondary flow? Does anybody know what the secondary flow means? Okay. Secondary flow. Secondary flow is this is U, right? This is U. And we have a secondary flow mean we have a V and W direction velocity. Okay, and some cross section even triangular. Okay, if you study the triangular flow around within the triangular, we may happen as a situation. We have a flow like this here. Okay, and so we have a secondary flow here. Okay, very near the corner here. Okay, you can check. Okay, so this is not mentioned or it's not inside this mathematical model. We don't assume any secondary flow here. Okay, however, some case may still have a secondary flow for some cross section. For the elliptic is okay, for the circular is okay, okay. But however, for the triangular, they may have a secondary flow. Okay. So this, okay, sometimes, okay, why this work and then it work for the triangular cross section, okay, this is a proof here, okay. Next, okay, we would like to talking about another physical problem. Okay, 下一个物理问题. Okay, is a flow between two rotational cylinder. Okay, we have a rotational cylinder and with the inner rotational cylinder and outer rotational cylinder. Okay, 所以我们有两个内边的跟内外壁的. Okay, so we have this is omega inner wall. We have outer wall. So inner wall is a rotational angular velocity is omega I. Outer wall is omega 0. Okay. So we try to find out the velocity profile within between these two, okay, region, inner flow, inner wall and outer wall. So we have the flow between two rotational cylinder. Okay. So this is an axis symmetry problem. Okay. So axis symmetry means is a partial theta equal to 0. We all don't. The velocity at any theta location should be the same, right? We take a velocity here, cross section here, to find out velocity profile, and velocity profile here, velocity profile should be the same. Okay, so any related to partial theta should be equal to 0. That's axis symmetry. And since this flow here, we have the rotational cylinder here. So we only have a v theta direction velocity. We don't have any vr and vz direction. So only the non-zero velocity component is v theta direction. Okay. So here is a complete cylindrical coordinate. Okay, r theta z. Okay. So we have the continuous equation r ur direction, u theta direction, and uz direction, and this is the plus operator for this cylindrical coordinate. So by applying this, okay, for this physical problem, we can assume this, right? So any term related to partial theta should be equal to 0. So here is a partial theta, and also the partial z is also equal to 0 because we only consider two-dimensional. The z direction we didn't consider at all. We consider all the same. So the velocity along the z direction didn't change. Okay. So any partial theta. So steady state. Okay. Okay, this should be assumed is a steady state here. Okay, so partial t is equal to 0, and then so ur is equal to 0, right? Since only u theta is the only component, so ur is equal to 0. So this is ur direction, but here we have u theta here, so this term will be okay survive here, and we have a minus partial p partial r. There's a pressure gradient in r direction. All these operators related to ur, right? This is all equal to 0. And this is x direction body force. We didn't consider body force. All the body force should be neglected. In theta direction, steady state, this term drop. U theta equal to 0. Not u theta, ur equal to 0. You have u theta, right? U theta is not equal to, but ur equal to 0. And this is a partial theta equal to 0, right? Any related to the theta direction variation should be equal to 0. uz is equal to 0. And u theta, ur is equal to 0. So this term all drop. Partial theta equal to 0. So this term drop. Okay. So this only term left is this term, these two terms,
and this is partial theta equal to negate body force. Z direction we didn't consider since only two-dimensional r theta only. Okay, we don't have any z component, so this is okay. So we may have this term here and this term here. So we can finally we can get our r momentum equation that's reduced from this, right? This equation. V theta square over r is equal to partial p partial r. So this is the equation we have. Okay, and 1 over rho here. Rho is here, right? So rho is divided. Okay, become 1 over rho. Okay, so that's an r momentum equation reduced to this. Okay, and this gives us what? Pressure gradient in r direction is related to what? Give you the so-called centripetal force. So V theta square over r is the centripetal force， 就离心力，对不对？所以这个地方 dPdr generate this centripetal force. Okay, so this is provide the centripetal force. Okay. And theta momentum equation reduced to this, right? This term. Okay, so the equation we have here, only these two terms survive. Okay, and this is Laplace operator should be applied to this. Okay, 所以我们基本上把它抄下来。Okay, this is our theta momentum equation. Okay, we only have V theta, and this is Laplace equation, Laplace operator from here. So Laplace U theta. So this is Laplace U theta. Okay, so it will be equal to this term, equal to what? Equal to our U theta over r squared. Okay, so this will give you this. Okay, and from here, as you can see, this is what? This is called equidimensional ODE. Okay, what's the equidimensional ODE? I think you learned that before, but you may forget. Okay, you may forget. Okay, this is the in engineering mathematics. Okay, we call this co-series oil flow, but you may more familiar with this is this form here, right? We have an equidimension x squared y double prime plus ax y prime plus by. So that's called equidimension. For this spatial ODE here, we have x squared and second derivative. First x to the first order and the first derivative, right? So we have this kind of, this is called equidimension. So solution form will be y equal to xm to the m order. Okay? So that's the formula we will use, okay? According to the ODE here. So we apply this mathematics, okay? We learn in the engineering mathematics here. So our solution form should be what? For this, we have the, as you can see here, this is the second derivative, right? This is dr, du theta dr. Okay, and we have r. When we multiply r squared here, it becomes r squared for this. Okay, and this is a constant. So we have the equidimensional. So we will assume our v theta is what? V theta is the r to the mth order. So this is the v theta is r to the alpha order. That's the solution form should be look like. Okay. 这个地方大家可以清楚为什么这个地方为什么 assume 这个就是从我们公数来的 ，OK。So we write down this could be the solution form for this ODE here, right? So we assume this V theta is to the alpha order, and substitute this V theta equal to alpha order into what? Into this equation here. Into this equation here. Okay, into this equation here. And we can find out our solution form. Okay, so you can find out alpha should be equal to positive negative 1. This is our constant alpha here. So we have a solution form like this. AR plus B over R. 所以你把这个 V theta substitute into this equation. Okay, and you should cancel most of the term. Only equation you got is alpha squared minus 1 equal to 0. You can check. Okay, 你可以 check 看看。Okay, So alpha will be equal to this. So our general form for this ODE solution, okay, equidimensional ODE solution will be the A is a constant times R plus B is a constant times over R. Since alpha equal to 1 is this, alpha equal to -1 is this. Okay, 就是它的 solution form for this ODE. So we have to, this A and B is what? A and B is a constant. So we have to apply what? Apply the boundary condition. Okay, we have two boundary conditions. One is on the inner wall, one is on the outer wall, right? So on the inner wall is R equal to R sub I. On the outer wall is a V theta at R equal to RO here. Okay, so R equal to RI, we have what? Velocity in the V theta direction is what? Since our rotational angular velocity rate is omega I here. So Ri times omega I give us V theta. Okay, so here we have a rotational here. So any point here is Ri times omega I. So give you the velocity in the theta direction here on the inner wall. Okay, similar on the outer wall here, we have the velocity V theta is Ro times omega O. So we have the two boundary conditions. Okay, and can solve this A and B. So this is A and B. We can find out. Okay, so we have a two boundary condition to solve this two constant, and by substitute these two constant back to this solution form, we can have a velocity distribution like this. So this is velocity. Okay, V theta is only function of R only. R is our variable, right? Is our coordinate system. The rest of it is just your boundary condition from your boundary condition or geometry. Okay, so that's a velocity profile. Okay, and by using this velocity profile, by substitute back to our R momentum equation, this is R momentum equation is from this equation here. So we already know the V theta, and we can find out the PDR. Okay, and also we can integrate. So this is from this. Okay, dPdr equal to rho V theta over R. So P we can integrate or get our pressure field. It's a function of R will give you this. Okay, so for this solution, okay, square, everything becomes square. Okay, this solution form is square and do the integration. Okay, and you can find out this. Okay, so this is a pressure gradient. Okay, can get integrate from this R direction momentum equation. Okay, and in our textbook, we have the problem 7.5 and 7.6. Okay, you can have a practice for this. They have shown some condition allow you to practice this. Okay, okay, we may use this as homework later. Okay, okay. Okay, that's okay for the. Okay, I think that's for this physical problem. Okay, we have the so-called rotational cylinder between the flow between two rotational cylinders. Okay, we can have this exact solution. Any question? Any problem? Okay, how to derive this, and then eventually you got this. Okay. Okay, okay, so we have still have a lot of okay. So next, okay, we will study so-called Stokes first problem. This is a very standard problem. Okay, Stokes first problem is we have a wall here, right? This bottom wall, but on the surface we don't have any upper surface. We only have a bottom wall, and flow is above this surface within this region here. And then this is the wall. Okay, 这是我们的墙壁下。So suddenly this wall will be at the time less than 0 is stationary, but suddenly at time equal to 0, our velocity on the wall, the boundary wall here suddenly has constant velocity moving here. So we have this step function. Okay, so this is time. This is our wall velocity. So the time less than 0 is equal to 0, and time greater than 0 is equal to a constant velocity. And we try to learn when we have this kind of step function for this boundary condition, what happened to the flow field on above. Okay, 所以我们想要了解一下，当你这个墙壁下列面墙壁刚开始不动的，突然让它变成一个 constant 这样移动，上面的流体要怎么动？ Okay, this is Stokes first problem. Okay, so this is the unsteady problem. Okay, so this is the one of very typical case is unsteady because it suddenly move, right? And our flow will change according to time. So this is unsteady problem. Again, since this plate is infinity plate, so any location here and any location here, at any x location, the velocity profile should be the same. So partial x should be equal to 0. Okay, partial x should be equal to 0. Okay, so any velocity gradient in acceleration should be equal to 0. And according to our continuity equation, partial u partial x equal plus partial v partial y equal to 0. Right? For the incompressible flow, so we have a partial u partial x plus partial v partial y equal to 0. Since partial x is equal to 0, right? Because it's infinity plate. And velocity profile at any x location should be the same. So we get the partial v partial y equal to 0. And v is what? It's a constant. And by the boundary condition we have that the y equal to 0 or v is non-significant is what? Sorry. Okay. Now I apply the y equal to infinity. Okay. Because the wall should change, right? Wall should change. Okay. 这个墙壁是会动，对不对？所以这些时间，所以 apply the flow in the far field. Okay. Apply the flow in the far field. The y go to infinity. Okay. Y go to infinity. Since only movement is on the surface here, far from the surface, the velocity should be equal to 0. Okay. Didn't disturb by this movement at all. Okay. So when y go to infinity, our velocity should be disappear. Okay, that's a physical. So according here, okay, v is a constant. V is a constant here. All the v velocity is all constant. Since here, since our v is equal to 0, y go to infinity. So our v, okay, v is what? V is equal to 0. Okay, v is equal to 0. Okay, we can use in the continuity equation to check. So we don't have any y component velocity for this flow field. We only have a u component or x component velocity. So we have a unsteady, okay, flow. So our Gaussian equation reduced to this. Okay, I think I should give you the full Navier-Stokes equation, and you can from here and you can reduce to this. Okay, and the full Navier-Stokes equation look like this at the beginning, like this. Right? It's this. Okay. So this is the velocity. Okay. So our u partial t is not equal to 0, right? And this term, the v is equal to 0, so this term drop. So we have this term here, right? And we all have the partial square u partial y square here, right? Because partial x is equal to 0. So only this term and this term survive. Okay, we don't have any pressure gradient term. Okay, since only so our velocity, our Gaussian equation for this physical problem reduced to this. Can you follow me? Okay. You should be able to do that. Okay, from the Gaussian equation, reduce according to the physical problem you have, the condition you have, and simplify your Gaussian equation. Okay, you should be able to do that. So this is our Gaussian equation. This Gaussian equation is very similar to so-called diffusion equation. If you change this velocity field, become concentration, and viscosity here become diffusion coefficient, become the so-called diffusion equation. Okay, 这是扩散方程式。Okay， 如果说你把这个 U 换成浓度的话。这个 nu 就是我们的 viscosity change to diffusivity or diffusion coefficient, and this is become concentration. So this equation will be called the diffusion equation. Okay, that will govern the diffusion, okay, of the concentration. Okay, So we have a Gaussian equation like this, okay? And our velocity, again, y go to infinity, our velocity should be approached to 0. That's one boundary condition. And second boundary